Screen is visible.
Yes.
Yes, sir.
Okay, thank you. So earlier we have seen that when a beam is subjected by some load, maybe point load or say UDL or any sort of loading, this load tends to deflect this beam section, and due to that deflection or the bending, some stresses gets generated in that beam, and that stress, we know that stress can be called as bending stress of a beam. And the equation was for a section sigma by y is equals to E by R is equals to M by I. Okay. Today we will see another kind of stress where some kind of normal stress and this bending stress can be summed up, and that will give us a nomenclature of combined stress. For that purpose, we will look for another structural member which is used in structural analysis to deploy the load coming from the superstructure to the foundation, and it is called column. We all have seen this sort of column in our houses. So what is the basic difference between this beam and this column? Yes, one thing you can say that beam always lies horizontally, where column lies vertically. But the most important difference is that if you remember the definition of beam, I said that the beam is a structural member which is acted by some loads which are in perpendicular direction to the beam axis. So the beam axis is the horizontal axis, right? Because it lies horizontally. Now the loads, whatever we have seen, those are acting perpendicularly or transverse direction with respect to the beam axis. So that was the definition of beam, and that was the characteristics of this beam structural member. Whereas for column, the load acts in the same axis of the member. That means if this is the axis of the column which will act vertically, the load coming from the other parts of the structural portion, it will come vertically to the column. That means it will act along the same axis of this column. So that is the basic difference between these two structural members of beam and column. So today we will see that when this sort of axial loading is acting, then what kind of stresses gets generated in a column and how we can calculate or read off that stresses. Now here, this particular load, say P, it is acting along the center line of the column or the axis of the column. Okay. For this case, if we want to see so what is this? This is the sectional view from the bottom side or say top side, anywhere is fine because this is basically a 3D member. So it will have its, and that case, if this P is acting at the midpoint, and if we want to see, if we cut a section over here horizontally, and if we want to see the section of this column, this load is acting nowhere at the center of the column. And due to this load acting at the very center of the column section, the stress which is generated due to this direct load will be nothing but an uniform stress. If this low area is A, the stress or intensity we can say as P by A, where P is the direct load acting at center and A is the area of a cross section. Then the stress below the cross section of the column is uniform as the load is distributed uniformly throughout the entire area. So the stress will be P by A. But in many times it happens that, say this is again a 2D view of a column. So many times it happens that the load coming from the superstructure, it is not acting at the very center line of the column. Rather, it acts at some distance, say E, distance away from the center line. So that means if we again want to see a sectional view, so now earlier the load was acting at the center point, now the load is acting at some distance from the center point. This is equals to E. If this happens, then the stress at this section, which was earlier a uniform stress, now it will not remain an uniform stress distribution. Rather, it will have some sort of non-uniform distribution. Means one side there is some maximum value, other side there will be some minimum value, and the stress distribution will vary from that minimum to maximum. So here the stress is non-uniform stress, whereas for this case it is uniform stress. This happens like this particular E, or the distance by which the load is acting from the center line, is known as eccentricity or eccentric distance. So the direct load coming from the superstructure is acting on a column at some distance. That distance is known as eccentricity or eccentric distance. And due to this eccentricity, the stresses which are getting generated in the column section is something like this non-uniform stress distribution, having a maximum value of the stress at one extreme point, one side of the column, and minimum stress at another side of the column. So today we will look into that case, that when this sort of eccentricity happens and when these maximum and minimum stresses are getting generated, so what is the value of this maximum stress and the minimum stress, and how these stresses, are they helping us in designing the column or they are in disadvantaged position? So we'll look into all those aspects. So let us redraw this portion here. This is I am assuming a rectangular section. That's why this rectangular cross section I have drawn. So this is P, this is E, again, this is E, the eccentric distance. Now, what are the loads are coming here? Now, as the load is compressive and acting in the normal direction, or the direct load is acting on this section, so due to this load, and if this area is A, one stress will be acting is direct stress, that is P by A. Let us denote it as P naught. So the one stress will be acting is the direct stress, as the load is acting perpendicular to this area. So the stresses is acting as direct stress. This is a uniform stress. But along with that, this P, as it is acting at a distance A, and say this axis is XX and YY, this P will have a moment, or will generate a moment about this XX axis. And due to that moment, so what is the value of the moment? The moment is P into E about, so moment about XX axis is M equals to P into E, that is having the moment. Now this moment is acting like this. So basically this moment is acting here, and this is the section. So the section is having some bending moment, and due to that some bending stresses will get generated. So this moment will give us some sort of bending stress on this section. So if this is our section which we have seen here, so this is affected by two things. One is the bending moment, and due to that the bending stress that is also acting perpendicularly on this section. Second is the load is acting on the section, and that is also having a perpendicular stress, that is direct stress. as these two stresses, that is this direct stress and this bending stress due to this moment, are acting similarly on a plane or on a section, these two can be algebraically summed up, or if it is some negative value, so they can be algebraically summed up. So either if it is both in the plus, they will sum it up. If one is minus, so one will be reduced from the other. But the main point is, as the both the stresses, this direct stress and this bending stress on a section can be summed up algebraically. What do we mean by this algebraically? Algebraically means they will consider the plus minus sign. Means if both the direct stress and bending stress, they are in the same direction, they will, both the cases it will have plus and they will add it up. If the direct stress and the bending stress, they are opposite in direction, then there will be a negative sign between these two and one stress will be reduced from the another value. So that's what this algebraically term is very important here. And also from the bending stress of a section, we know that one part will be compressive in nature and other part will be tensile in nature. So for this case, due to this application, this portion will have some compressive case because it is the load is acting and this is having here, and for this case it will have some tensile stress. So for this case we may add this portion, the direct, whenever both the stresses are in compressive zone, we will add it up, the direct stress and the bending stress. However, when the bending stress is the tensile portion, that area, but in that zone, we will reduce that bending stress from the direct stress. Why this compressive and tensile are coming due to the bending part? Let me go back to here. If you remember this plot, so this is happening the bending of the beam, right? This was a beam portion, the element was there, this was a section, this was our bending moment, and due to this application of bending moment, the stresses are getting generated. And if you remember that this is we call neutral axis, so the upper portion was given as the compressive stresses and in this portion it is the tensile stresses. So whenever the direct stress is acting here in direction, so the compressive stress and the direct stress will be summed it up. However, when again the direct stress will be acting only one direction, but in this case the tensile stress is acting in opposite direction of the direct stress. Okay, so that's why we will reduce this portion. Now this is, we are looking for a beam, so just if we rotate the entire portion vertically, say this is in horizontal, right? So if you just look it from the vertically, you will see this portion here where the direct stress is acting on a section and this bending stress is acting both in compressive and tensile in nature. So now what is the bending stress quantity? The bending stress due to the moment P into E on a section is, what is the equation of a bending stress? If we know the bending moment, you remember this M by I into Y, sigma by Y equal to E by R is equals to M by I. So if we just connect this one and this one, the bending stress is happening M by I into Y, and this is at a point Y from the neutral axis, and the neutral axis is XX axis. So this was the neutral axis, and that's what the bending moment is occurring. So at any distance y from the neutral axis, the bending stress is happening like this M by I into y, where the M is the moment acting on the section, that means this one. So P into E, I into Y, where I is the moment of inertia of the section about neutral axis, or here XX axis. So this is the XX axis, and this distance is E, and so P into E, that's where the moment is acting, and due to that the stresses are getting generated, and this is the Y is the distance of any layer from the neutral axis. Now, as I have written here clearly that we can sum it up this algebraically, we have to introduce the plus minus sign here in the bending stress. Plus minus sign, why? Because if this bending stress is of compressive nature, then we will use the plus bending stress, as it is in the same direction with the direct stress. But if it is in tensile in nature, that portion, so for that portion where the bending stress is tensile in nature, for that portion we will reduce this bending stress from the direct stress. So from direct stress, we see that this is P naught, if is denoted, is nothing but P by A, whereas the second component of the stress is bending stress, and let's say denote it as plus minus M by I into Y, or we can just substitute this M as P into E by I into Y. Okay. Now we will see that how, when these two are summing it up or added up, how it is giving us the resultant stress, and when these two are reducing or from each other, then how the resultant stress is looking like. So let me rewrite this part again. So here it is P naught, or direct stress, is P by A, and here it is P equals to bending stress plus minus m by I into y equals to same as plus minus p into e by I into y. Now, bending stress. Now, this direct stress is uniform, but this bending stress varies with this value y, and if the y value is 0, that is at the neutral axis, the bending stress is 0, and if the y value is the maximum or the outer layer of the section, then this value gives us the maximum bending stress both for compressive and tensile nature. So that means maximum stress due to bending occurs at the extremities of the section. Extremities means at the two outer layers. So if this is our section and this is the neutral axis, so here and here, these two are the extremities. So in these two cases, the stresses due to the bending will be maximum. Maybe be maximum, and here it will be 0. To look for the maximum amount of bending stress, let us now where the maximum amount of bending stress will occur. For y equals to y max, P will be the P max. Let's denote it as, say, PB. B denotes the bending, okay? So that means maximum bending stress PB will be equals to plus minus P into E by I into Y max, because the stresses will be maximum when the Y is Y max. Now the maximum bending stress is denoted as PB, so it is equals to plus minus PE by I into Y max. Okay. Now this Y max by an I, we have already introduced a term. What is that? Sorry for the noise, okay? This is happening outside. Okay, so what is this Y and this Y max? How they can connect it to each other? Anyone? Am I audible?
Yes, sir. Yes, sir.
Okay. So we have done it in the bending portion for beam, na? What is the connection between this I and this Y max? Also, we have done similar thing in the torsion of shaft as
Bending
well.
modulus.
Bending modulus, that was the term. नोटबुक में रहेगा, एक बार देख लो. You forgot already. नोटबुक में है क्या? I by Y max को क्या बोलते हैं?
Z something.
Z something, no? Z. And what is
Polar modulus.
polar modulus was used for torsion of shaft. because there we used the polar moment of inertia. But when we use the I and Y maximum or any ultimate layer, Z is fine because the polar modulus nomenclature was ZP. The P comes from the polar part. Nobody can remember the terminology I by Y max. Section modulus, you remember?
Yes, sir.
You have already forgotten this part so quickly. Okay, so this is the Z, where Z is the section modulus and this is I by Y max. Means, so this, I guess you remember this part that the sigma max is equals to m into z, because whenever this y becomes y maximum, sigma also, that is the bending stress, becomes the maximum value, and then we have used these equations to either to find out the bending moment, and the moment also becomes the maximum moment. So we have done some numerical problem as well. So the z is the section modulus when the beam is in bending position, and that time it is a sectional property because only dimensions are required to find out this z or the section modulus, where I is the moment of inertia of the section about the neutral axis, and y max is the maximum distance of the outer surface or outer point from the neutral axis. Okay, so now if the y max, if we move here below I, so this becomes I by y max. That means we can replace it as Z. So the maximum bending stress which is occurring at the two extremities of a section is plus minus P into E by Z, and the direct stress is occurring here, the P by A, that is the uniform stress. So P naught, that is the direct stress, is P by A, and this PB, that is bending stress, we are considering the maximum one so that we can get the total value. So plus minus P into E by Z. So this is the uniform. So this is both maximum and minimum are same. There is some plus and minus due to the compressive nature and the tensile nature. So in the very first slide we have seen that if this is that column portion we are looking from here, say, so this was the non-uniform stress distribution. I told that one is maximum value and another is minimum value. So now we can say that maximum stress occurring at one of the extremities occurring at one of the extremities, that means here is P by A plus P into E by Z, because here it was the compressive and this portion was the compressive part, whereas the P minimum is P by A minus P into E by Z, and that is happening here. So for this case, the P maximum is happening here. This is the algebraic sum up of the direct stress and the bending stress, maximum bending stress, because we are talking about the extremities of a section. There is the maximum distance from the neutral axis. Neutral axis also, here we have denoted at xx. And here it is the P minimum, because here this portion will be make a minus sign will use, and that will be deducted from the direct stress. So this was this maximum values of the stress and the minimum values of the stress, but this may have three different conditions. So we will look into that part now. So first, let me write down again. This P max is P naught plus PB, that is P by A plus P into E by Z. This P minimum is P naught minus PB, that is P by A minus P into E by Z. Condition 1 says if this P naught is greater than PB, if this P naught is greater than PB, what happens? This will be positive because both are summed up, so this is positive. This P minimum, as this portion is greater than this, so this will also be a positive value. So how we can draw that? So let us draw the bottom of the column. We are not drawing the entire column here. So we have done the section part. So here we are trying to draw the stress distribution. So as this P naught is a uniform stress, so this will be entirely uniform, entirely for the section. So this part is P naught. Now it says this P naught is greater than the PB part. So P maximum, the PB portion will sum it up. So this is the PB portion, will sum it up at here, where the similar amount will go this side because that is being reduced. So if we just connect it here, now this portion is the opposite direction. So eventually So this one, it says this one is our PB, and this one we can say as P maximum, and this portion we can say as P minimum. So you understood what happened? Initially, we have drawn the uniform stress, that is P naught, which is P by A, this portion and this portion. For this extreme point, as it is both the cases are in compressive in nature, so we have added it up, this PB portion PE by Z. So we have added it this portion. Whereas for this case, the similar amount has been deducted. So this deducted amount, this PA by A minus PE by Z, will tell us the P minimum, whereas these two plus will tell us the P maximum. Okay? So this is the condition 1, if the P naught is greater than PB. What if P naught is equals to PB? What happens then? What will happen if P naught is equals to PB? What will be the value of P max?
0.
P max
2 times P naught.
and P minimum is
Always 0.
0. How we'll draw that portion? So again, the beam section bottom part is drawn. So this case, the direct stress is occurring here. Uniform is P naught, and this case here, the equal amount will be acting here, and here the equal amount will be deducting this part. So basically, so this part is our PB, and here this is basically P naught minus PB, so it's a 0 case. So here it is P max, and here it is P minimum. So if the P naught is greater than PB, then some sort of P minimum value remains there and P max is obviously there. If the P naught is equals to the PB, that is direct stress is equals to the bending stress, one portion it is twice the direct stress or bending stress, as both are in same magnitude, so twice of the stress. Other part it will remain as 0. So the stress distribution will vary from 0 to twice P naught, and here it will vary from P minimum to P max. Now another condition left is that if the P naught is less than PB. You understood this portion? Any doubt? Any question?
No, sir.
Yes, bolo. Okay, you said no. Acha. So we are going for the third condition, that is if P naught is less than PB. So what happens? Let me write down the formula here. P naught plus PB, P by A plus P into E by Z. P minimum is P naught minus PB, P by A minus P into E by Z. So what happens if this P naught is less than PB? Let me draw this portion again. So this is the column section. At bottom, we are trying to draw the stress distribution. So initially, the direct stress will be uniform as it is. So this is our P naught. Now, here P naught is less than the PB, so bending stress is of higher value of the direct stress. So whatever the P naught case, so it will be some portion higher than the, so this is PB portion. So similarly, this portion will get reduced. Now, if we join these two portion, it will be a straight line. So here, what will happen basically? So this is P naught, the uniform stress. This was PB, which is of higher magnitude as compared to P naught. So it is added up. This is P max, where this becomes now negative because this is become higher than this one. So this is a negative. Negative means this will go in the opposite direction. So now this portion, as we are adding up, because this portion were in compressive zone, now this is going in the another direction. That means this portion, this small triangle by this red color and the black one, is nothing but in tensile zone. So the stresses below this column, one part is in compressive zone and small part of it is in tensile zone. Whereas for these two conditions, for say condition 1, both the stresses were in compressive zone as none of that were in the opposite direction. And here, although one extremities is starting from 0, but still none of the zone is going in the tensile part. So everything remains in compressive zone. Here, some part is going in the tensile zone and some part remains in the compressive zone. Now, when we design a column, so what is the column does? The column is this vertical section. This transfers the load to the foundation system, and this foundation rests on the soil. Okay, Now the soil cannot take tension. So whenever the stresses are getting generated here like this, so some tension is happening here, the soil here cannot take that stress, and that is very dangerous for the whole structure, and due to that the several cracks can come up in the structure. So the civil engineer or the structural engineer or say any soil engineer, they always try to keep the stress which is coming due to the superstructural load from top to remain it in the compressive zone. So tension is, we always try to avoid this tension zone. So as an engineer, we want to find out the load in such a way so that the stresses are getting generated that is in the compressive zone. Now from these three conditions, which conditions will give us the entire compressive zone? What is the condition then if we talk about this P naught and PB? For what condition the entire stress remains in compressive?
P naught greater than PB.
Sorry,
P naught greater than PB.
P naught greater than PB, but P naught equals to PB is also giving us the compressive, right?
Yes, sir. Yes, sir.
So P naught greater than equals to PB is the condition for which the entire portion will be in compressive. So because both the cases are giving us the compressive part. Whereas if we go for this condition, it will give us the tensile zone, and that we do not want. Yes, any question? Please ask.
No, sir. No, sir.
Can you please repeat?
No, sir.
Acha. So to be in compressive, the P naught should be equals to PB, or PB should be less than equals to P naught. What is the expression for PB? PE by Z. So PE by Z. What is the expression for this direct stress? P naught, P by A. So P by A. P cannot be 0, so we are omitting each other. So E less than equals to Z by A. So this is the condition for which the entire stress will be, or I should say the resultant stress. Resultant means resultant of direct stress and bending stress will be in compressive zone. So this is the condition, that is the eccentricity. What is E? If we say this is the column, this is the column central line, the P is acting here, and this is the distance E. So this E should be equals to less than equals to the ratio of Z by A, where Z is section modulus of a section and A is area of that section. So as an engineer, our job will be to find out this value of eccentricity, where E is nothing but the eccentricity, eccentricity or eccentric distance, eccentric distance So our job is to find out the eccentricity or the eccentric distance in such a way that the entire stress will be in compressive zone. So if we have a rectangular section, say there is a rectangular section here, say this is B and this is A. This is the x-x axis. This is y-y axis. So this is P and this is the distance E. So this is a rectangular section of A and B. So what will be the E value for which the EX value, that is distance from the X axis, that is a neutral axis, for which the entire stress will be in compressive zone. So what this EX is nothing but Z by A. So what will be the EX, that is this point from the X axis?
B by 6.
B by 6. Good. But for others, let me do it. So Z is, what will be the Z then? As you said, B by 6. What will be the Z then?
So 1 by 12 BQ.
Z.
Yes, sir.
What is Z? Ix by the maximum Y. What is Ix? Ix means about x-axis. What is the moment of inertia about x-axis?
1 by 12.
Bolo?
So 1 by 12.
1 by 12.
Yes, sir.
And then bas wahi?
So BQ into A.
1 by 12 B cube into A. He is saying AB cube. Okay. Is he right? Or it will be the opposite? Any other one? Anyone else? Is he right, or it will be 1 by 12 a cube b?
ठीक है सर.
ठीक
ठीक
है,
है सर.
चलो मैं भी मान लेता हूँ, ठीक है. Then what is the y max?
B by 2.
B by 2.
B by 2.
Yes, good. Then z will be a b cube by 12 by b by 2. That means a b square by 6. Now what is the value of a? AB, simply AB, yeah. So what is the value of EX then? Z by A is equals to AB square by 6 by AB, B by 6, as he rightly
B
said
by 6.
initially. So this is the EX value of, for this case, B by 6. Means the load P, this may act any distance away from the x-axis, the distance being b by 6. So here it is acting in this direction, so it is the b by 6 distance it should be. If the load acts here, then this will be compressive and this will be tensile. So here also the same part or same law is implied, that is b by 6 happens. Now if the load is acting about eccentrically about this x-axis, means along this x-axis, okay, say here it is acting, or say here it is acting. So what will be the distance here then for this case?
A by 6.
A by 6.
Good, a by 6, and this portion will be a by 6. So I am redrawing this part here clearly. So this is the rectangular portion, okay. This is our y, this is our x, this is b, this is a. So we have seen it here, b by 6, b by 6, a by 6, a by 6. So let us draw the vertex point here. So this point is 0, a by 6.
B by 6.
Yeah. Sorry, yeah. 0, b by 6. This point will be 0 minus b by 6. This point is a by 6, 0, and this point is minus a by 6, 0. So if we just connect this dot, so this is giving us a shape of rhombus. So this is giving a shape of rhombus, and what it says, this particular shape for a rectangular section is known as core or kernel of the section. core or kernel of the section, right? Now, so what happens? The load P, like here it was acting, the load P, if the load acts anywhere between this core or kernel portion, it will give us the entire compressive stress. But however, if the load acts somewhere outside of this kernel section or the core section, then some amount of tensile stress will appear. So, as a designer, our job will be to find out the core or the kernel of a particular section, and then we can say that whatever load is coming, keep the application of the load within that core or the kernel of this section. If that goes outside of this section, then tensile stress will generate and that will be dangerous for the structure. So that is our job here, to find out the core or the kernel of the section. Now, this is B/6 from here to here. This is B/6 from here to here. So if we find out this portion, what is this amount? What is this amount? This is B/6, this is B/6.
B/3.
B/3. Then what will be this amount? And what will be this amount?
5B/6.
Huh?
5B/6.
5B/6. Why? This is total B. This portion is B/3. So this, if the entire B is divided by 3 sections, one is B/3, what will happen for the other two? The B/3 is the middle portion. Then what will happen for the other two parts? Will it not be B/3?
B/3, sir.
Huh? Because this is happening in the middle portion. If this was in the outer side, then we would have been different type of sections. But as it is in the middle section, these two sections has to be B/3, B/3. Similarly, this portion is A/3, again middle portion, middle third, and this is also A/3. This is now we can see the core or the kernel of the section remains at the middle third of a rectangular section. This is known as middle third rule for a rectangular section. So this rule or the middle third is very unique only for rectangular section. If we have any other type of section, this rhombus shape or the middle third rule will not be valid. Okay, so don't take it as a complete generalized part for the all sort of sections. No, it is only for a rectangular section. The middle third rule, that means the core of the kernel of the section will lie at the middle third portion. That's why the middle third rule for a rectangular section. Okay, so any doubt till now? for this theoretical discussion of combined stress? Is it fine?
Yes, sir.
Okay. So if it is asked that, say, one load is acting at any point with some eccentric distance, then if you are asked to find out the bending stress and the direct stress, then if you are asked to find out the core or the kernel of the section, please use this way. And I hope you have written down the formulas along with me, right? Then,
Yes, sir.
yeah, yeah. And also there are three different conditions. If it is asked that for which conditions, and if suppose you are asked that draw the stress distribution diagram, then please draw like this as I have shown here. One will be uniform, other will be plus minus. That's so you can find out. No need to remember these parts, because if you want to remember ना तो उसमें गलती आएगा. Remember मत करो, समझने मतलब try to understand, then it will be easier. Okay. So if it is fine, then I am unsharing this part. We will take attendance and then we will do some numerical problem in the later part of the class. Okay. I have shared the attendance link. Please give your attendance and don't leave after the class, because it's a 2-hour class. We will do some numerical problem. So your attendance is done. Anyone left? So I am stopping the attendance now, and let me reshare the screen. Is it visible now? The screen is visible?
Yes, sir.
Huh?
Yes, sir, visible.
Okay.
Yes, sir.
Okay. So now, if we have a solid circular section of diameter d, what is the core or kernel of the section? If the circular section is of diameter d, what will be the core or kernel of the section? So how we can proceed? How we can proceed? What is the formula we have to use? Anyone?
ई निकालना पड़ेगा सर पहले
ई
ई निकालना पड़ेगा सर
ई निकालना पड़ेगा। ई कैसे निकालोगे?
ई इक्वल टू जेड बाई ए
E less than equals to Z by A. Good. So we need to find out the Z, that is section modulus of this section, circular section, and A is area of the section. So what is the Z then? You tell me.
आई बाई वाई मैक्स
I by Y max. Okay. Then if we know the diameter, can I find out the expression of Z? What is the expression for Z then in terms of diameter?
So pi d cube by 16.
Pi d cube by 16. Okay. Is it correct? Anyone else? Is it correct? बोलो. उसने सही बोला पाई डी क्यूब बाई 16 ये सही आंसर है या गलत आंसर है?
सही है सर।
सही है।
यस सर, सही है सर।
So what is the Z? I by Y max.
16
I कितना है?
गलत थे सर, गलत थे सर।
I कितना है?
ये वेट हो जाएगा सर, इसलिए भाई डी स्क्वायर बाई 8
हाँ, I is
बाई डी क्यूब बाई 16।
I is pi d4 by pi d4 by 64, right? No, yes, pi d4 by 64, and okay, this y max is d by 2, so z is pi d cube by 32 ना? समझ में आया कहाँ पे मिस्टेक्स हुआ जिसने 16 बोला था?
Yes, sir.
Okay, so what is a?
यस सर, यस।
क्या कर रहे हो?
Pi d square by 4 because it's in diameter. Then what will be the z by a?
The D by 8.
D by 8. So E should be less than equals to D by 8. So E anywhere, this is circular section. Anywhere if the E is within this D by 8 part, then that is the core or the kernel of this section. So if here to here is D by 8, and here to here again D by 8, here to here again it is D by 8, and here also D by, because it is a circular section. Can you please mute yourself?
सॉरी सर,
thank-
सॉरी सर।
Okay, no, it's okay. Thank you. So this is D by 8, 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 and everywhere it remains same. So if we connect this portion by this way, so this is our core or kernel for this solid circular section, where here to here is, sorry, it will be D by 8, and here to here is again D by 8. So what is the diameter of this core? Is D by 4, right? Because D by 8 divides radius D by 4. So again the middle portion is giving us a quarter portion of the total diameter is D by 4. So this is denoted as middle quarter rule for circular section. So middle quarter rule means because this is the 1/4 of the entire diameter and that is occurring at the middle part. So this is the middle quarter rule for this circular section, which is a solid circular section. Now, if we just extend this to case, like this is for a solid rectangular part and this is for a solid circular part, just we want to see that if we have a hollow section here, then how we will react. So if we have a if we have a hollow section here, whose outer diameter is d naught and inner diameter is di, so what will be the core or kernel? Or rather just try to find out the eccentric distance. Go by the definitions, then गलतियां नहीं होगा, miscalculation नहीं होगा. What will be the Z value for this hollow section?
So pi by 32 or d naught की power 4 minus di की power 4.
Very good. We have done similar kind of part in our one problem we have done in torsion. So where also we have done the similar kind of thing. So just for others, I am just quickly repeat the process. So if we have the entire solid part of d naught, what is the I value? Pi d to the power, what is the I value? That is pi d to the power 4 by 64. And for this square part, it is pi di to the power 4, not square, this portion of di, not di, pi di to the power 4 by 64. So as it's a hollow section, so we reduce the inner moment of inertia from the outer one. So I naught minus I, and then it will become like this. Then we have divided the y max, which is the maximum distance of the outer surface, that is d naught by 2, and that it gives us pi by 32 d naught into d naught to the power 4 minus di to the power 4. So, and what is this a? A already we know because it's a simpler part, pi by 4 d naught square by di square. So what will be this E should be less than equals to
पूछा जाए बाधा
बोलो।
V by A.
Mm-hmm. D by 8. Will it be just D by 8?
pi by 4 d naught square minus di square.
और एक बार बोलो।
1 by 8 d
Hmm.
naught square plus di square upon d naught square minus di square into 1 by d naught.
ओके ओके, नो नो नो, इतना कुछ तो नहीं होगा, मतलब सम पार्ट्स आर ओके, कुछ तुमने एक्स्ट्रा बोला। क्या एक्स्ट्रा बोला? व्हाट इज दिस?
ऐसे ऐसे नीचे वाला खत्म हो गया।
राइट। So this portion is d naught square plus di square into d naught square minus di square.
di square yes sir.
So that part will get cancelled.
Cancelled yes sir.
So E will be, and here this pi will get cancelled. 4 will get cancelled. So y 1 by 8 d naught upon here it will be d naught square minus di square. Is it coming, everyone?
सब प्लस होएगा.
Yes, plus होगा, sorry.
Plus sir plus.
Plus होगा, yeah. So E less than equals to d naught square plus di square by 8 d naught. Okay, that is the E value. So if I ask you from here, what should be the radius of this core or kernel for hollow circular section? Yes, what was the radius? Yeah, what was the radius? For a hollow circular section, if we know this part, E less than equals to this part, what will be the radius of the core or kernel of the section?
d naught square plus di square upon 16 d naught.
16 d naught. इसीलिए मैंने पूछा था यहाँ पे कितना था रेडियस? What was the value of E here?
D by 8.
8. रेडियस कितना था?
D by 8.
यहाँ से भी तो d by 8 की तरफ जाएगा, यहाँ पे भी तो d by 8 ही जाएगा ना, तो दोनों मिला के d by 4 आता है. So
Yes sir.
जो for circular section, whatever the z by a, that is the radius of the core or kernel. So don't get confused with that. Suddenly if asked that what is the radius of the core section, so this is the value of your core section. This is the value of radius of your core section. Now if suddenly asked that what is the diameter of the core section, then what you will do?
So multiply.
What will be the diameter value of the core section then? Just
E.
Q into this part. That's what we have done, na? The E less than equals to d by 8. So d by 8 from, so d by 8 from here to here, and this d by 8 from here to here. So total is d by 4. So diameter of the core section is d by 4. Radius was d by 8. So similarly, this is the radius of core section. Radius of core of the hollow circular shaft. Okay, and if you ask the find out the diameter, then simply it will be 2 into this part, that means d naught square plus di square by 4 d naught. Okay, so if we want to draw this part so that you can remember, this is our hollow circular section, and this is the core section. So the diameter is square d naught square plus di square. What was the value? 8 d naught. So 8 d naught. So 2 into that part. That means d naught square plus di square by 4 d naught. So this is the diameter of the core for hollow circular section. Okay, now coming to the last part of today's problem is that if we have a hollow rectangular section, if we have a hollow rectangular section, say this is x, this is y, and this is b, this portion is small b, this small it is d, and this is capital D. So what kernel, or what will be the E value?
One by six.
1/6 of what? Then आगे
Capital B cube minus small db cube upon b.
just 1 minute. 1/6 then
Capital DB cube.
capital BD cube,
DB sir, DB cube.
DB cube. Okay, that's it.
Minus small db cube
Okay,
upon b.
अरे यहाँ पे ब्रैकेट खत्म. Okay, हाँ,
Capital B
capital B
into
into
small d, capital DB minus small db.
यही ना, ये ठीक है तुम जो बोला.
Yes sir.
हाँ, कहाँ पे होगा ये? मतलब अबाउट व्हिच एक्सिस?
x-axis sir.
About x-axis means about x-axis मतलब y-axis के ऊपर होगा ये point और x-axis के
x-axis के
ऊपर
ऊपर होगा सर, x-axis के ऊपर.
होगा. And what about the other case? You have to find out 2e na, because here it is a rectangular section. Actually, very good. You have done it quickly.
y-axis के लिए सर.
बोलो.
1/6
हम्म
bd cube.
Smaller cap. अच्छा.
Capital
Yes.
minus small bd cube upon d.
Then
d into d
अच्छा d
into bd minus
d minus bd.
bd is same.
Good. Very good. So others are also getting.
Yes, sir.
Yes, sir.
Okay. So shall I do it, or shall I do it, or it is fine for others? If you want, I can do it. Do this part. No issues. Let me do it now quickly so that कोई दिक्कत नहीं है, जल्दी कर लेते हैं. So this part is what it is says that this ixx. So ixx means about x-axis. That means what is happening? B d cube by 12 minus b d cube by 12. Okay, y max is our d by 2. So zxx is basically b d cube minus b d cube by 6d. So this is our z max, and area is nothing but area was bd minus bd. So what he has done, just he has divided this portion by this, and that's what this is zx. So about axis, so this portion y was our ey. So this was ey, and this was ex, right? Because yeah, this portion was ex. So it's the easy part. Just we have to find out the section modulus, and then area is the same. Just the change will be the dbq or bdq. Okay. So everyone got that?
Yes, sir.
So yeah. Okay. If any doubt, anything, any question? If no, then we can leave. Or if you have, then you can ask.
Thank you, sir.
What happened? Yeah. Okay.